Hi guys, welcome back to Data Every Day. Today we're looking at a data set of different forests or trees. Basically it's data about tree observations from 4 areas in the Roosevelt National Forest in Colorado. And you'll notice that the data set has already been pre-processed for us. I believe we have our categorical one-hot columns that were already encoded, so everything is in numerical form. And it's ready to be ready to fit some models on it. However, there is an issue, which is that we have a terrible class imbalance here. So today I'm going to try to go over some methods that can be used to deal with class imbalance and make your models better at performing within each class. Alright, so let's hop into the notebook. We're going to use a logistic regression model to make our predictions. But first we have to deal with the imbalanced classes. So I'm just going to go ahead and import these. I'm also updating Seaborn because there was an issue later with the pie chart that I just need the latest version for. I'm just going to hide the output from here. And alright, now let's load in the data using pandas.readcsv. And we can grab the file path right over here, covertype.csv, paste that in, and take a look. So it's there actually are a decent number of examples here. We have 581,000 rows. So there's I guess the first thing I'd like to do, there's actually one thing I want to do before we move on. If we take a look at the cover type column, that's what we're trying to predict here. If we look at the value counts, so this is how many in each class. You can see we have 28,000, actually no, that's 283,000 in class 2, 211,000 in class 1, and then all the way down at the bottom in class 4 we have only 2,700. So there's a real big difference here, and it's going to negatively affect the way our model performs. Now, one thing I just want to note before we move on, you'll note that this starts from 1 up till 7. So there are 7 classes, but I'd rather it start from 0. It seems to work more nicely, especially if you're because most of the indexing in Python starts from 0. It's just nice to have the classes start from 0. So what I'm going to do is take the column. I'll just copy this actually, and I'm just going to subtract 1 from it. That will subtract 1 element-wise from each value, so that everything will get shifted down. The 1 will go to 0, the 7 will go to 6, and that's all it will do. You'll see now we have 0 through 6. So we still have the 7 classes with the same distribution, but now the indexing has been changed. So I'll just comment that, start class labels from 0 rather than 1. Okay. Now let's deal with this imbalanced data. So what I'm going to do is first I'm going to, can I spell this? First I'm going to train it on just with the imbalanced data to show you how the model is not performing so well. And then we're going to try 2 different methods that can be used to correct the problem. So let's look at the class distribution. Now I'm just going to visualize it as a pie chart just so that it's nice. So what we'll do is create a new matplotlib figure. Fig size 8 by 8, and then plot.py. So we're going to plot the value counts themselves. So I'll paste that in, and we'll do dot values just so that we're only getting. Actually, no, I'm going to just keep it like that. Actually, no, we'll keep values on there. Then colors. I want to give it a nice color. So I'm just going to create a new color map at the top from Seaborn. So if you ever want to convert a Seaborn color palette into a matplotlib color map, you can get the color palette from Seaborn like this. I'm going to use the set2 color palette, which looks nice for this purpose, and you enable as CMap equals true. Now the reason I updated Seaborn at the top is because this wasn't supported in a previous version, so keeping that. Then we're going to initialize it once it's been created with, so we specify a number of colors to take from the color palette. So I'm going to take 7 because there are 7 classes. Then for colors, we'll just pass in CMap. Okay, then labels. The labels, we're just going to grab, we just want these as the labels, right? In that order also. So I'm just going to grab this, but instead of values, I'm going to do keys, which will just give us these. Yeah, you'll notice if I run that, this is the keys only, so that will be our labels. And then we'll also put on an auto %, which will just show percentage values on the pie chart for each of the classes. So we'll format it like this. So I'm displaying to 1 decimal place. And then I also want a % sign at the end. Okay, then plt.title, class distribution, and plt.show. Alright, so this is what we're working with. You can see how underrepresented some of these classes are. We have very close to half of the data in the 1 class, and then we have a large portion, just over a third, in the 0 class, and then the rest are really just minority classes that are not, so there's not a lot of examples in it, so the model will not have experience dealing with these ones. It will just become so used to dealing with 1 and 0 that these will just become, that the performance within these categories are most likely just gonna tank. So let's create some helper functions moving forward. So I want to create 3 different models with 3 different sets of the data. So I'm going to create some functions that I can apply to each set. So I guess we could call it split and scale, which will just take in a data frame, and we'll start by making a copy of the data frame, and we'll split df into x and y. So y will be always, it will be the cover type column. So this is what we're trying to predict. So I'm just going to make a copy of that. And then x is going to be everything except the cover type column. So I'm dropping it from axis 1. Oh, sorry, this should not have axis 1 there. My bad. We're dropping it from axis 1 and making a copy. So now we have our y and our x that have been split off. And then we'll do a train test split. So I didn't actually go over the imports at the top. I should real quick. I'm using NumPy and Pandas, as you can see, and then matplotlib.pyplot and seaborn for visualization. Then the standard scalar and train test split function from sklearn for preprocessing. I'll use the logistic regression model just to see the performance. As our model, right? And then we'll use the confusion matrix and classification report to analyze the results of the model. So now I'm going to do the train test split. So this function from sklearn allows us to split the data the same way. So we're going to split x and y the same way so that we have 2 sets, a train set and a test set. X train, x test, y train, y test. And we can include a train size to specify how much of it we want in the train set. So I'm going to do 70%. And we'll also include a random state. This function also shuffles the data, so the random state will ensure that it's always shuffled the same way. Okay, and then we'll scale. So we're going to scale x with a standard scalar. So we'll create a new scalar object, standard scalar. That's from sklearn as well. Standard scalar will just give each column in x a mean 0 and variance of 1. So it will allow each of the columns to take on a very similar range of values, and that can perform improve the performance of many models. So I'm going to fit the scalar to the train set. Then I'm going to transform both the train set and the test set based on the fit we had to the train set. So scalar.transform xtrain. This will return a NumPy array, so I'm going to turn it back into a data frame afterwards. And that will be important later. So the column names I'm going to keep as the old column names. And that's going to be our new xtrain. Then very similarly, we'll do it for xtest as well. Note we only fit to the train set, but we transform both using that fit. So this is test and this is test. Alright, and yeah, this doesn't matter so much, but we'll make it test also. Alright, and then we'll return xtrain, xtest, ytrain, and ytest. Alright, so I guess we could just preview what that looks like. This will be the training with the imbalanced data. So we'll have, why don't we make imbalanced data will just be a copy of our data. So I want to make 3 copies, that's why I'm just creating an extra copy. And then we'll get xtrain, xtest, ytrain, and ytest from our split and scale function. We're passing in imbalanced data as the df here. Oh, I misspelled it. Okay. And now we can see xtrain, this is all of our data here. Well, there's actually less of this is 70% of the data, and the test set contains the other 30%. And you'll notice that all the columns have been scaled to have mean 0 and univariance. Then our y, so ytrain, this is what we're trying to predict, it's just the class descriptions. Alright, so I want one more, well, I guess I can train it in the meantime. So we'll create model 1. This will be a logistic regression model that's going to, this will just be like our baseline model that we're training on just the data as it is without any sort of techniques employed to try to deal with the imbalanced classes. So I'm creating the model, and then we're going to fit the model, model1.fit, on the train set. Xtrain, ytrain. And while that's fitting, I'm going to create another function here that's going to be evaluate model. And this is going to take in a model, a class balance. This is just a string that's going to say like what method I used here. And then passing in xtest and ytest. So we'll get the accuracy for the model, which will be model.score on xtest, ytest. And then we can print it out. So this will just be a function that sort of returns a bunch of like results from the model. So the accuracy, I'm going to include the class balance string in here. So I'm just putting it in parentheses like that. And then we will also include the accuracy value displayed to 2 decimal places with a % after it. So we're doing dot format, and then we're passing in the class balance to the first location, and the model acc times 100 to the second location. Doing times 100 because I want to see it as a percentage. Then ypred, so I'm going to create some predictions from the model. We'll get that simply with model.predict xtest. So these will be our predictions, and then we'll create a confusion matrix we'll call it CM with the confusion matrix from sklearn. We're comparing the actual answers ytest to the predicted values that we just got. And very similarly, we will do a classification report we'll call it CLR, which also compares the two. That's also from sklearn. Okay, and then we want to plot the confusion matrix. So I'm going to create a new matplotlib figure. Fig size of 8x8. Seaborn heat map. So this is a heat map that's going to show us the confusion matrix. So we pass in CM, turn on annotations. We're going to format it like so to ensure that the counts for each of the classifications is shown as integers rather than in scientific notation. And setting the minimum value on the color map to 0, turning off the color bar, and I'll give it a color map of blues. Alright, then on the X label, I want to have it predicted, and on the Y label is the actuals, and then we'll give it a title. Confusion matrix. And we'll show it. And then after that, I want to print out the classification report underneath. So I'm going to put a bunch of these, and then the CLR after that. Okay, so that's it. That will return the accuracy, the confusion matrix, and the classification report for a given model. So our fit is complete. Let's call evaluate model on the model 1. We're going to pass in imbalanced as our class balance, and we're passing in xtest and ytest. So here's our accuracy. At a glance, it looks like maybe this model's not doing so badly. A 72% accuracy, that's reasonable. But if we look at the confusion matrix, we can see that all of our accurate predictions are over here. And you'll see that as we go on, especially class 4, this is the one where we had very few examples. We barely doing well. Look, we have a whole lot of classifications for 1, but the actual value, we only got 17. So if we look over in class 4, we have a recall of 1%, well, 0.01. This is saying out of all of the actual values for the class 4, we got 1% of them correct. So, not good, right? We're doing quite well in these two categories, which are the really highly represented ones, right? 0 and 1. You can see that we have a lot of true positives in 0 and a lot of true positives in the 1. But we're also misclassifying between the two pretty badly. Well, it's not terrible, but it's, you know, you can see we have a huge disconnect between the overrepresented classes and the underrepresented classes. All right, so now let's do something. Let's try first we're going to try undersampling, and then we're going to try oversampling. So I have a picture here. I did not make this picture, but I got it from Kaggle. That someone else posted it in a notebook. I believe he was named Raphael Alenkar, and basically this is saying the difference between undersampling and oversampling. So in both cases we have a huge majority class and a small minority class. And in undersampling, we're going to basically only use as many examples from the majority class as we have examples in the minority class. So we lose a whole lot of data, but in the end we have a 50-50 split. On the other hand, oversampling is saying let's duplicate, let's sample with replacement as many times as we need to get to sort of artificially boost up the number of minority class examples. So both of these methods have their drawbacks. For undersampling, you can see we're losing a tremendous amount of information that might be useful for training a good model that can generalize to unseen examples. And on the oversampling side, we're also training on duplicate and fabricated data. So that also may affect the model's ability to generalize to new examples. So we're going to do both and compare the results. I'm going to start off with undersampling. So we're basically just going to use only here. Why don't we do this? Okay, so this is training with undersampling. So I'm going to create a new copy of the data called undersampled data, and that will be data.copy. So let's just take a look at the value counts again. And I just want to get it for the cover type column. So you can see if we're going to undersample down to the least represented class, that's this one. That means at the end we should have all of the classes should have 2,747 examples. Right? Does that make sense? Yeah. Okay, wait, class 3 is the least represented. I was saying class 4 before, but looks like class 3. Interesting. Yeah, we did worse in class 4 than in class 3. Interesting to note. Why is there only 866 examples here? Wait, is that correct? Oh yeah, no, that makes sense. Never mind, sorry. Okay, so back to this. Basically, like I said, each class we're going to remove examples. We're going to sample 2,747 examples from each class, so that in the end we have we'll have a perfect class distribution. So let me get the min class size. So the min class size is 2747, but we can get that programmatically by taking the minimum of this, right? Maybe dot values. Then we can take a look at what it is. You can see we got just that value. That's the minimum one. So let's just print out. Wait, what happened? Okay. Hold on. Dot values, and then print size of smallest class. Min class size. Alright, so we're going to shrink down all the other classes down to this size. And I'm going to undersample the majority classes. So what I'm going to do is create this class subsets list. And class subsets is going to be a list of each portion of the data for a given class. So what I mean is, let's look at the original dataset, for example. We have all these different cover types here. So if we call data.query and we pass in a query for cover type equals 1, then we'll get all the examples, which here is 283,000, where all the where the cover type is 1. So, we could change this to 5, and then we get all the cover type 5 examples, right? And so if we do this for 3, which is the least represented, we only get 27,400. So what I'm going to do is I'm going to separate all these different subsets of the data into a list. And so to do that, we're just going to say, okay, for I in range 7, because we have 7 classes, we're going to get undersampled data, which is this right here, dot query, cover type equals, and then I'm going to concatenate the string of I. So we're actually just going to substitute in I from 0 through 6. So this will give us, if we look at class subset sub 0, see the first element of class subsets is all the 0 cover types. The second one is all the 1 cover types, all the way up to the 7th one, which is all the 6 cover types. So now what we're going to do is go through each class subset and sample, sort of redefine it as, we're going to sample 2747 examples from each class subset and then reassign it to that subset, if that makes sense. So for I in range 7, so for each class subset sub I equals class subsets sub I dot sample min class size. So the dot sample function, if you want to look at it, here's our data. If we do data.sample 10, it will get 10 random rows from the dataset. Okay, I also want to note that we can also include replace. By default, replace is false, which means sample without replacement, which means once you draw a sample, you can't sample the same sample again via the function. So we can also turn this to true, and I doubt we're going to get any duplicates here, but if true, this means sample with replacement. So we take one, and then we put the copy back. So we're just copying examples, but we can still draw the same examples. So for undersampling, we want replace on false, because we don't want to take the same examples. We want to, obviously we don't want duplicates if we can avoid them. But when we do oversampling, we're going to have replace on true so that we can constantly be duplicating rows as we need. So here we're sampling not 10, but min class size examples, which is 2747. And we'll also include a random state in the sample function, just so that it always samples the same way when we run the notebook. And then at the end, so let's actually run this. And now if we look at class subsets, class subset sub 0, you can see we have 2747. Class subset sub 1, we have 2747. 2, we have 2747. We actually have the same number of examples in each subset, but the classes are still preserved. So then the last thing to do is let's take all these subsets and concatenate them back together into one data frame using pandas.concat class subsets axis 0. Axis 0 means we'll stack them on top of each other rather than left to right. And then after we do that, we want to shuffle the data, because if we stack them as they are, we'll have all the zeros on top, then all the ones, then all the twos, and so on. So we want to shuffle it again. Let me think. I realize we probably don't actually have to shuffle it, because we have this function that shuffles it for us with the train test split function. It's not necessary. But I guess I will just shuffle it. So to shuffle it is you can actually just use the sample function also, but this time we include a fractional value of 1.0. So this is saying sample 100% of the data set without replacement, which is the same as shuffling the data. But we'll include a random state here as well. And then after we shuffle it, let's reset the index on the data frame with drop equals true to prevent the old indices from becoming the new column. And that will be undersampled data. So this is our new undersampled data. This is the final form of it. If we take a look at it, you can see we now have 9,229, and the reason for that is what was it, 2747 to the power of 7. Sorry, that's not how you do power in Python. Sorry, it's not to the power of, what's wrong with me? Times 7 is that number. So we have 7 sets of 2747 examples, and in fact, if we look at the value counts for undersampled data, oh, sorry, let me just get it for the cover type column. You'll see that we have a perfect balance now, 2747 in each example. Now, this is nice, but we have much less data now. I believe we had like 500,000 originally, right? 581,000 examples originally. Now we're down to only 19,000. So, you know, there's a drawback there, but on the other hand, let's see how the model does. So I'm going to now create a new xtrain, xtest, ytrain, and ytest using the function we had, which was split and scale, right? Split and scale. This time I'm going to pass in undersampled data. And then I'm going to create a new model, model 2, which will be another logistic regression model. And we're going to fit model 2 to the train set, xtrain, ytrain. Alright, then we'll call our evaluate model function, passing in model 2. We're going to pass in the string here will be undersampling. And we'll pass in xtest and ytest. So, okay, we actually got a slightly lower accuracy value. So if you see up here, we did have a 72% accuracy. Now we're down to a 70% accuracy. But if you look at the confusion matrix, you'll see our model's doing much, much better across classes. So you can see that the dark blues represent high values. So all of our values, like the highest values, are all in the right spots, which is this diagonal here. These are the true positives for each class. These on the side are our misclassifications. So it looks like we did much better across each class. If we look back at this, you can see we had some really high F1 scores, which are just a combination of precision and recall. But then we had some really dismal ones. Down here, though, we have pretty decent F1 scores all across the board. And it looks like our worst class here was class 1, which originally was actually the most represented class. So that's interesting. And you can see in class 1 we had a recall of, or a precision of 60%. That's saying out of all of our predicted values for 1, which is this column here, 60% of them lied in the correct value. So, alright, that's good. Last thing I want to do, it's actually bugging me. Look, we're missing 3 hyphens there. This is just, I'm just going to go up and put those in. Okay. There we go. Alright, so, last thing we're going to do now is oversample. So this is training with oversampling. And for oversampling, we're also going to make a copy of the data. Oversampled data is data.copy. And let's take a look at the value counts again. Actually, just from the cover type column. So this is the same as always. We have these 2 classes that are just dominating, but now the challenge is not to reduce everything down to 2747, but to bring everything up to 283,301. So like in this picture, you can see we're sort of making copies to artificially boost the number of minority class examples. So I'm going to get a max class size, which will just be the maximum of this, right? We just want this value. So dot values, and then numpy.max. And let's print it out. Size of largest class. Max class size. So it's 283,301. So now let's actually perform the oversampling. I'm again going to create class subsets. So let me just grab that. Let me just grab this whole code and I'll edit it. So instead now we are oversampling the minority classes. Minority. Okay, and our class subsets will be a list of all of the queried portions of the data for each class, like we had before. So if we run this, we take a look at class subsets, just the first one. This is the original 2747 one we have. Oh, what's going on here? This isn't right. Oh, okay. It's because I used undersampled data. I need to use oversampled data, which is just our fresh copy. Okay, here we go. So here we have different number of examples for each class. So this is all the ones. Then we have, for example, in 3 we have all the 3s. And we want to artificially inflate all the minority classes. So what we'll do is do this, which is what we did before. Before we took each subset and we sampled min class size samples from each one. Now the only difference here is now I want to sample max class size samples. Now if we're sampling a number of samples that's greater than there are entries in a data frame, we have to make sure that we have replace equals true on. This way, after we draw a sample, we'll put it back. And so we don't run out of samples going down past the maximum possible samples. So I should actually probably include this up before, right here. This will be replace equals false. And then down here we have replace equals true. So at the end of this, every single class should have 283,301 samples. So now we're going to overwrite oversampled data, and that's going to be a concatenation of the class subsets like we did before. We're then going to shuffle the data and reset the index. So I'll run this, and let's take a look at oversampled data. You can see this one's taking quite a bit longer than the other one. Now we have 1.9 million examples. And if we look at the value counts of just the cover type column, you'll see that every class has 283,301 examples. Alright, so last thing to do is just run it through our functions again. So xtrain, xtest, ytrain, ytest equals train test split. No, sorry, what's it called? Split and scale, that's our function. Passing in now oversampled data. Right. Then we'll create a third model. This will be model 3, also a logistic regression model. And we'll fit it to the train set. Now this is going to take just a moment, so I'll pause the video and resume it when it completes. Alright, it finished training, and now we will call our evaluate model function on model 3 with a class size, this is the class balance, which will now be oversampling. And we will pass in xtest and ytest. And we get a accuracy very, very similar to oversampling, to undersampling. And if we take a look, we'll see that, well, it's about the same sort of performance. It's not bad. It looks like maybe these values are slightly darker. It's about the same. It's performing the same way in the same classes, right? Only thing is the scale is different here. Yeah, it looks like in both classes, class 3 and class 6 are doing the best, and the others are not so bad either. In terms of F1 scores, it looks pretty similar. Lowest here is a 56, highest is an 88. If we look up here, lowest here is a 58, highest is an 89. So very similar. Maybe this one performed a little better, but also this one has had more data. However, it is fabricated data. So like I said, there's a drawback to both of these, but I would definitely consider a model that can do this as much more effective than a model that can do this, which is what we had for the first model. Oh, what happened here? 22%. That's not right, is it? That can't be. Oh wait, what's going on here? We got a 70% accuracy before. Maybe this is the problem. I'll run this again. Okay, yeah, that's better. Yeah, so this is not doing the job. We have a high accuracy value, but the model's performance is very poor, right? Because this doesn't do what we're asking the model to do, which is let's actually predict the cover type. And so this model is very good at predicting one of these two cover types, either a cover type of 0 or a cover type of 1, but it completely fails to do the task for all the others. Down here, though, we have a nice distribution in both of them. However, like I said, there are drawbacks to both approaches. So that will sum up today's video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.